video, I will discuss about line integral of vector point function. The line integral of a vector point function vector fxy along a curve C is the integral of component of vector f along tangent to the curve C with respect to the infinitesimal length of the curve. Let's understand this with a figure. Here in the xy plane I have drawn the curve C, and on this curve I have located a point P whose position vector is vector r, and at this point the vector point function f can be represented as vector f equals fxi cap plus fyj cap. The infinitesimal change in the position vector of point P, vector dr equals vector dxi cap plus dyj cap. The infinitesimal length of the curve at this point is ds, which equals modulus of vector dr. The component of vector f along the curve at this point can be obtained by making dot product of vector f with unit vector along tangent at this point, which is vector f dot vector dr upon ds. The line integral is the integral of this component with respect to ds along the curve C. This can also be written as vector f dot dr integral along C. Now let's discuss about application of line integral. First application is work done by a force. The vector f is a bearing force which is represented by vector f equals 2x square yi cap plus 3xyj cap. The curve along which the particle is displaced from its initial position to final position is y equals 4x square, and it is drawn on this figure. The line integral of vector f along this curve from initial point to final point gives the work done. So we write the work done equals integral vector f dot vector dr along this curve, and on making the dot product we obtain integral along the curve 2x square y dx plus 3xy dy. We change the y and dy variable to x and dx variable using the curve equation, and we obtain the integral as the integral from 0 to 1 2x square multiplied by 4x square dx plus 3x multiplied by 4x square multiplied by 8x dx. On integration we obtain 104 upon 5, which is the work done by the force in displacing the particle from its initial position to the final position. The second application is in obtaining the circulation. A fluid moving in xy plane has the velocity field represented by vector v. The circulation of this vector along any orbit closed curve C is called the circulation. The circulation of this vector v is obtained by obtaining the line integral along this closed curve of vector v, and this circulation represents the rotational property of vector v, and if circulation is 0 we can say that fluid velocity is irrotational. With this I am ending this video lecture. Thank you for watching.